Good morning, everybody, and thank you so much for being here. I think, Professor Soga, it's an honor to present after you. It's like a dream, so thank you so much. And what you put forward in the first presentation, especially towards the end, was really reimagining what the world could be. Because I think today on sites, on construction sites, across the world where we monitor, where we survey, where our technology partners bring these really cool drones, etc., distributed fiber optics, we don't look at the simulation side of things. We don't look at how can we make infrastructure assets more sustainable and safe for the future generations. So I think that was my biggest takeaway, that today intelligence exists and technologies exist, and it's up to us on how we come together as a community to find solutions to enable the future. So today I'm going to take you through a quick session. It's titled From Micro to Macro, on how we enter the age of decision intelligence on the field, through a few case studies on a few projects we've been working on, and our approach called Infinitus 2.0. So today, as Professor Soga also stated, we have the ability to detect millimeters of strain across thousands of kilometers of pipelines in San Francisco. We do vibration monitoring at scale. We can measure from space, we can measure from underground, but we have so much data. What the technology in our industry has enabled is a lot more data, a lot more dashboards, a lot more softwares, but less clarity. Today, on projects, what matters to you as an asset owner, as a consultant, as a construction company is my project finishing on time? Am I overspending? Am I spending less? And is the value being given to the people post-construction and to my organization as well? So through this presentation, I want to raise 3 takeaways. One is that today, there are ways to get more clarity, to save you time, to save budget, and to have a more integrated ecosystem of infrastructure. Second, that it is possible, and I think Professor Soga shared it already, to do this with today's technology. There's a lot of data points. It's not that simple, but it is possible today. And third, that it's happening around us in San Francisco, in London, like we saw at the Canary Wharf, and also in the Middle East, in Dubai and Saudi. So the biggest takeaway that we've seen with a lot of infrastructure projects, and I think what happened in China a few months ago with the bridge collapsing, with the landslide happening and the bridge being evacuated before the landslide, was a very, very valuable example of monitoring. And today, the gap that we see is that the data is extremely fragmented. And last year, we came to the conclusion of integration, and the responsibility is diffused. Because pre-construction, it's up to the testing companies to come in and submit a report to Mr. Asset Owner. During construction, it's up to the monitoring companies, the consultants, to make sure the asset is safe. And post-construction, for most of the assets, there is no monitoring. So the asset is living, and it's like a human being stepping out of college into the real world, trying to figure it out for themselves without any mentors, without any job. So we really leave our assets alone in the wild. So how do we go from into the wild to really enabling those simulations and predictive to archive the data, not lose memory, and make assets last longer and safer? So the journey that we've come to today in our industry is that there's a lot of awareness. There's a lot of ways to collect data. There's a lot of understanding. We have domain experts in this room from across the region, and we know the mathematics and statistics that go into construction monitoring. We started doing it from paper to Excel to platforms to now even ChatGPT assisting in them. Now we're reaching a stage of intelligence. How do we get decision intelligence on assets at scale before we reach how every mature industry reaches governance? How do we govern assets and city systems at scale? So today we're in phase 3, and to do this phase, in this phase we have a 4-step process on how we bring intelligence at scale. So the first phase we call is Skywatch, And Professor Soga showed an example of INSAR monitoring through satellites. And I'm going to take you through how we can monitor hundreds of assets at scale and enable you to prioritize. Because as an asset owner, what matters to you is prioritizing the assets you need to maintain to save cost and time. As a consultant, what matters to you is to prioritize the design and the work that you're doing with the contractors. And as contractors, you guys have thousands of things on your head. You have thousands of companies that you're subcontracting, like Etihad Rail coming up. You have so many things to manage. How do we enable you to prioritize the decisions you need to make? And typically we have a meeting every day at the end of the project where we take the big printout of the compliance report, about 100 pages with so many graphs, and we sit down and see what happened. Instead of that, imagine you getting notifications like you do from your mobile phone telling you, based on the data today, based on the construction data, these are the 3 people you need to call and ask what happened. So we're moving from figuring it out and taking decisions reactively to proactively monitoring. So how does prioritization happen from Skywatch? There's 4 major technologies that we integrate. One is INSAR, second is LiDAR, and there's drones, mobile mapping, etc. that's enabled this today, photogrammetry, and of course climate and optical data, because in today's world it's just not about the geotechnical data, but also the environmental data that today we can get from satellites. Like yesterday we were sitting with Majid and he said that there's this startup launching satellites and prioritizing weather data at district level. Now, if we can integrate that real-time climate data with the monitoring data of an asset, it enables you to see a larger perspective. So again, INSAR, LiDAR, photogrammetry, climate, and optical data. So imagine Dubai's metro systems today. What we've done as a pilot, we've taken the city-scale INSAR baseline for the city of Dubai. During the Blue Line project that we're working on, we're taking continuous ground sensor data and surveying at station level, TBM data, etc. And we're trying to build unified decision intelligence across the asset by integrating all of this data and giving contextual insights. But for this part of the presentation, I want to focus on the Blue Line INSAR pilot that we have done and submit it to Murad, so we have to discuss this after. But what this has enabled the client to do is prioritize where to look and when to look. So we divided the area into 14 zones, looked at over 302 buildings in the city of Dubai across 20 stations to enable building level asset screening to give decision intelligence. Typically, what in our scope we would do is send surveyors and survey every building, 300 buildings, sending so many surveyors, so much time. And then the buildings that flagged, we would install instruments. Instead of that, spend a couple of hours, run algorithms, process the satellite data, zone it, and then work along with the INSAR data and the ground data, validate it, and then prioritize the survey. So saving time both on the construction company side and the monitoring side. So this is the alignment, and that's just the satellite overlay of the INSAR study. And in INSAR, typically red means settlement, blue means uplift, green means it's all good. But on the pilot, we first had to prove that the technology works. So how do you monitor something from space on the ground and give millimeter level settlement? People are used to laser scanners because you can see it, and sensors, because with sensors you have calibration sheets. So what we did was we got the GCP, the ground control point data, from this time period of the study, and we validated our INSAR results with the ground control point data. And what we found was we had the accuracy about plus minus 3 to 6 millimeters between the stable ground control point data provided by the client and the INSAR data. And this enabled us to acquire the data, process the data, validate the data, extract the building points, and classify stability. And what we found that most buildings were stable. The highways had a little bit of instability, and open ground had variable context-dependent analysis. So the biggest takeaway is that today, if we have hundreds of kilometers to monitor, today as a mine owner, as a building owner, today if you have hundreds of buildings to monitor, we can screen from space, we can integrate 10 to 15 ground control points in critical areas to improve the accuracy and help you prioritize which areas to look at. So this is just a sample graph of excavation areas shared historically by the client and the stable ground control point. And you can clearly see the satellite data along with the seasonability, which we mitigate, is very stable on the ground control point. And you can clearly see that the excavation period was from 2023 up till, because it was still going on during the construction. So we did this correctiveness, and we ran a few analysis to get the large scale 3 to 6 millimeter accuracy. And then we reran the INSAR data with the more accurate result. And what we really found was, after the accuracy, we gave the clients a way to prioritize where to monitor and how. So for each zone, we have the number of buildings and the overall risk score dependent on the average mean and the endpoints of the data. So as you can see, the critical zones that we found were from Dragon Mart to International City 2 and International City 2 to 3, with the 11 and 7 buildings there. And in most areas, we're seeing a very low to moderate risk, which we will now validate with the ground instruments. And these are some examples of a few buildings on the old type of report. And today, we just tell you which zones to look at and prioritize. And for example, now, as a project manager, you know which buildings there are. A quick insight: moderate substance, moderate high. What's the definition? What's the trend? And what's the likely cause? So what we've enabled through this project is that we can go from satellite acquisition to deformation mapping in phase 1, which was awareness. In phase 2, we can also do asset classification and ground correlation. But now in phase 3, which is decision intelligence, we can enable someone who's managing a very, very complicated project across a city to prioritize the zones that need to be monitored through risk maps, alerts, and enabling them to see what happened where. Now, this is another interesting project we're doing with Dr. Marwan and the Infrastructure Ministry. And here again, there's this road in Fujairah with landslide and rockfall susceptibility. And Dr. Marwan called Amit and I, and he said, where do I install your instruments? Which instruments do I install? Because he's done a lot of work with open ground to classify the geology. He's done a lot of work with photogrammetry surveys. And the end goal was to build a machine learning alert system to dynamically manage the opening and closing of the roads and predict the health of the road. So we said, okay, the easiest way to install our various IPIs, etc., and prioritize is, let's go back in time. Let us look at how the ground has moved and prioritize zones for installation. So once again, we took INSAR and we distributed the results into 7 key monitoring zones. We had the maximum deformation of about 147 mm in one zone, and we recommended 15 areas to instrument in this unknown area from before. So through the INSAR study, these were the zones across the road that we identified to prioritize instrumentation, but something happened. There was a lot of vegetation in the area, which enabled us to think beyond just INSAR, because INSAR with vegetation doesn't really work well. So here we decided to integrate other remote sensing parameters from satellites to validate the results more. So we followed this AHP framework, and we looked at the vegetation index, water index, distance to road, distance to fault, looked at the soil moisture, looked at the rainfall, looked at the temperature, looked at all of this environmental data and other contextual data, followed the AHP framework to make our validation a lot stronger from the INSAR. And what this enabled us to do is, so this is just a one-day image of the building index, vegetation index, water index of the area historically. And an interesting observation we also had is that this is the historical rainfall from 2022 to 2025 versus land surface temperature. And that is the soil moisture data we got from satellites. So if you can see in 2022, it's mostly dry, less red. 2024, more red. And you can clearly see the difference in rainfall in 2022 and 2024. So we did a lot of cross-validation through algorithms. This is the easiest way to visualize it. And we gave it weights. So the weights of the slope, the elevation, curvature, lithology aspect, to then again give a susceptibility zone map in the area. So 2 ways of remote sensing to validate our results. And what this helped us do was that it helped us come down from 7 zones to 5 zones. Validate our results, 5 zones were exactly the same as before, and we omitted 2 more zones. So saving costs, saving time, enabling prioritization. And to go back, we again classified those zones as critical zones, moderate zones, and stable zones. Now, we gave a beautiful location map to Dr. Marwan to install the instruments. But where are we going from here? Wait. Sorry. Yeah. So where we're going from here is that we're now taking 5 zones, sorry, there's 6 written here, those 5 zones, taking the remote sensing data, installing instruments like inclinometers, piezometers to get the ground data with more accuracy, and then after 3 to 6 months of getting that ground data, building a predictive model on the safety of the road and landslide area and road closures. So it saved us a lot of time, and this awareness enabled us to prioritize. So I've shared 2 examples on awareness, and what it really helps you do is prioritize. But what remote sensing alone does not do is it does not tell you the risk. It enables you to understand where to look. But it does not tell you this thing is going to collapse tomorrow. So whether we're doing INSAR, whether we're doing photogrammetry, whether we're doing drones, whether we're doing LiDAR, today we have a tool to monitor assets at scale and get awareness and have the first phase. So if the biggest takeaway from the first part of my session was prioritization, what do you do after you prioritize? So today, as Professor Shoga shared, there's a lot of technologies. There's remote sensing, there's geodetic systems, there's fiber optics, there's instrumentation, there's seismic and vibration monitoring, there's environmental monitoring. And last year at the end of Save the Bio, we came to the conclusion of integration. And after we integrate, what we need to do is converge this data. Because each layer answers a different question. And it's very easy to take an analogy of the human body and infrastructure. For you, your blood pressure, your cholesterol, your temperature, your calcium gives you different insights about your body. And depending on your age, where you're born, what food you eat, what kind of socioeconomic background you come for, it does affect your lifespan. So in the same way, looking at various parameters of infrastructure, bringing them into one integrated space and converging and working with domain experts. Because today, to classify that I have some health issue, I need a doctor who's a specialist in radiology to look at me. So in the same way, to take this integrated data, we need a specialist geotechnical engineer, a specialist in buildings to help validate and build a deeper foundation. So you know where to prioritize, you have the domain expert, you have the machine learning, now let's find a solution. So I'm going to take one example, because in Dubai we have super tall towers, we don't see them in many places, and we're going to look at Jeddah Tower and deeper, but I just wanted to mention Burj is easy because here again the foundation monitoring has been very, very critical. But why super tall is different? The number of piles, the foundation, the shafts, the depth, but also when it comes to monitoring, something unique that we do is we monitor the verticality of the building. Is it going up in the way that it's designed? Because there's so many effects, even the sun affects the building as it goes up. Day to day, like the Burj Khalifa is like a sundial. It moves in a circle depending on where the sun is. The time, again, structures don't fail suddenly. They fail over time. Precision, here you cannot do prioritization with even 1 centimeter or 5 mm from satellites. You need that 1 millimeter precision when you're going up to a kilometer height. And our approach was really for the Jeddah tower to do settlement and displacement, wind and thermal effect correlation on the tower while it's being constructed. Because what we realized in Jeddah was wind and temperature are the most critical environmental parameters to take in along with the instrumentation and surveying data. And we built a GNSS, geodetic reference network. And as you can see, the technologies used here were GNSS, total stations, inclinometers. We did some surveying with digital leveling. And we fused this data. And we did a few algorithms like RTK processing, etc. And these are a few pictures from site with our surveyors using various technologies. And the conclusion that we came to was that we have enabled the asset owner to almost complete a 1 kilometer tower, which is unheard of. The consultants on the job to validate a design that was unbelievable, like how do you build a kilometer high tower? And the monitoring companies and the surveying companies and the construction companies to complete projects on time, even though the project was delayed for other reasons, with about plus minus 2 mm of positional accuracy through the GNSS network. That's the confidence that they have in the data. The asset owner can sleep peacefully at night with this surveying network. And what the flow we again followed was, we collect the data from GNSS inclinometers, we integrate all this data into one platform, we analyze this data using some machine learning like least squares, etc. We build various alerts that are dynamic based on the project conditions, and we give decision intelligence. What is the action you need to take? What do you need to do tomorrow? Instead of looking at a bunch of graphs, project manager, call surveyor, call X person to solve X problem. Another interesting example is the Anjikhat Bridge in India. So it's the only cable stay bridge, and it's about 1,000 feet above the ground in the mountains in the Himalayas, lots of wind. And the consultants there told us to install 220 sensors to monitor the health. But here we, again, through studying the data, learned how to prioritize. But there's a very special sensor called an accelerometer, which measures vibration. That helped us take that prioritization into decision intelligence. But first, we started with INSAR and did a 3-year study. And we looked at the critical areas on the bridge. And you can clearly see red here. And this is where the heavy pylon was constructed and validated our approach again. And we prioritized monitoring the slope, which was not in the initial plan of the monitoring. So they added total stations to monitor the slope along with some IPIs. So this enabled context off the bridge, which could have caused problem on the bridge. We prioritized zone A, zone B, and did analysis. And after that, on the accelerometer specs, it was take 100 samples per second, 24/7 hours a day, on accelerometers and measure the data in G, acceleration due to gravity. If you do the math, that's a lot of TB of data a day. For an engineer to analyze, machine learning can do it, but for anyone to analyze. So with chairman here, we started studying acceleration on a bridge. And we realized that every bridge has a frequency. And if we convert the raw G data to a fast Fourier transform, we can get the signature of a bridge. And for that, guess how much data we need? 1 minute of data, 200 samples once a day. And if we measure the change of FFT every day or before and after an event, that is good enough. Because if there's an earthquake and the frequency of the bridge before or after stays the same, that means there has been no damage. And to go a little bit deeper, we had accelerometers on the left side and the right side of the bridge. So if the FFT or the signature of the bridge matches on the left side and the right side, you know that in between there are no issues. So in the more technical terms, we took the raw data at 200 hertz, did some filtering, and then looked at the structural fingerprint of the asset. This is where they're installed. We have 6 sensors. And what's interesting is that when we compared left side and right side over a period of 6 months, we had a match on the first station of about 99.5% on the FFT curves, on the second one of about 95.8%, and on the third curve of about 96.9%. Now that level of confidence really enabled us to say that the bridge in the structural health monitoring is doing well with 6 sensors and 1 algorithm. When the consultants, no offense to any of them, suggested 220 sensors on the bridge. And this is a sample graph where you can see the peak frequencies are the same, and the estimated natural frequency during train movement on the 7th of June was the same for all. Here there was a little bit of electrical noise on 1.27, and we basically then started analyzing train event responses because the Indian Railways has about 23 million passengers. And we took this study to the Indian Railway Ministry. And last week we were also sitting with them to say, how do we monitor those 100,000 aging bridges at scale? Prioritize with INSAR, and then install accelerometers with GNSS to validate the INSAR and improve the accuracy, and see how, and the ones that show a change in left, right, or in frequency over time, heavily instrument them based on the design. And this is another example on the pairs. So this is how we, in the initial studies, looked at the pairs. Now we take it through a software. But you can see the peak frequency, left side, right side, left side, right side, left side, right side. So 5 is on the left, 6 is on the right, is almost the same. And the peak frequency of each and every sensor matched through the bridge. And when we took it through time, this is the one from June 7th to July 22, you can see that on 2 pairs of the sensors, at an average, the line match is the same, and on top, the line match is the same. So once a day at similar times, you can really see the change of trend with some noise. And the noise, when there's noise, then we take data from the other sensors to analyze the noise. Some of them is due to heavy loads. Some of them is due to high wind events. Like the maximum wind speed we've got is about 180 kilometers per hour. It's a lot of wind. So this is something that we can take across structures. A simple formula to look at raw vibration, convert it into a frequency domain, look at the structural stage, converge it with other parameters if there is an issue, to give decision intelligence. This can be used in buildings, on bridges, on dams, on mines. So something simple can add a lot of value post-prioritization. So what integration has enabled us? What is in it for everyone in this room? Why does intelligence matter post-integration? Because it distinguishes response from forcing. We've been on projects. I mean, Amit, Vikas in this room get a call from the project managers all the time saying, sensor, what does this data mean, etc. Let's find a way to proactively monitor our projects so that we can monitor more with less. Separate cause from effect, because as Professor Soga clearly said, we design for 100 years, but the design is never really for 100 years. So how do we actually look at the asset, what the reality is, and take action to enable it to last for 100 years? And if it's not working, preserve the data from the foundation and reuse the foundation, because the foundation is very expensive. And remove doubt and not just add data. Today we need to understand that we have the ability to prioritize, we have the ability to integrate, we have the ability to simulate. But just getting more data without a domain need is pointless. On some critical structures like the Wanzabeel Tower, you needed that type of data because it was extremely complicated. On simple bridges, on simple buildings where people live day to day, access to commute, you don't need that complicated instrumentation. A simple fiber optic cable, a simple accelerometer, remote sensing to prioritize where to look can be the answer for asset owners and contractors. So we have the tools, we have the domain experts, we have the data. What we never had today as an industry was the system for decisions. And as Marjorie said yesterday, bad data, bad decisions, good data, good decisions. And as a framework that we use in most projects now is we collect the data. We can collect it from earth to sky. We integrate this data into one platform with context. It's not just the sensor data. It's what was the design, what is the environmental context. We analyze this data through ML, AI, statistics, even basic math work sometimes, but run application-specific workflows. Because for a building, for a cable-stay bridge versus a concrete bridge, the analysis is so different. For a high-rise building in Dubai versus a high-rise building in San Francisco, the analysis is so different. The nature of the ground is so different. The need of monitoring is so different. Then we get insight through the machine learning backed by human judgment. And I think this is something that Professor Soga really emphasized on, that today we can get all the data analyzed through AI. But at the end of the day, it's human judgment of the data that enables us to take those decisions faster. So instead of you going through the data to come up with a decision, we give you 3 options and you pick X, Y, Z, this is the decision I need to take. And we get decision intelligence. And the blueprint really that that we're emphasizing as an ecosystem of asset owners, consultants, contractors, academia, technology companies sitting inside this room is we need decision intelligence at scale. We want you to prioritize those decisions on site. We don't want you to go through hundreds of pages of compliance reports. We don't want you to go and run simulations to analyze the data once the incident has happened. We want you to monitor at scale and prolong the asset life cycle, enable your projects to finish on time. We want human judgment to become more powerful with more context. The more we know as humans, the more we learn, the more we're exposed in our day-to-day lives, the better decisions we can make. So the more data we have, the more data we integrate with context, of course, the better decisions we can make during our projects. Fusion and intelligence. Today, all of us run houses, all of us run organizations. We all want that intelligence dashboard for our company. We all want that data. How do we do it for our infrastructure assets as a system, at a city scale and at an asset scale? And data sources. Today, I think some of the drones out there, the satellites, distributed fiber optics, traditional instrumentation like accelerometers, piezometers, it all exists. And today, what's happening in the world through robotics, through machine learning, through AI, enables us to do this, not only in cities like Dubai, but also in places where people can't afford this infrastructure monitoring. Because I think looking at the other side is also very critical. And just a short note on AI, because what AI excels at is detecting patterns, ranking assets, helping you prioritize, helping you take decisions. But in regulated infrastructure and through the experience that we've had with the machine learning, one takeaway has been that AI has not replaced the engineers, but it's enabled engineers to become better engineers today. And that is the gift that we have. How do we take all this data and make better decisions? And a very, very simplified flow for projects today is, again, that 5 things that I said: collect, analyze, collect, integrate, analyze, insight, decision intelligence. A key box to add is human judgment, because that box enables us to make smarter decisions at scale. So through this session, I think we've talked about prioritization and monitoring at scale. We've talked about integration, how we can integrate any data. If you have a railway system, we can use the satellites and tell you where to look at. If you have 100 buildings in Dubai, we can figure out which buildings to prioritize. If you have a road network, we can embed fiber optics and analyze the traffic. Be aware, prioritize. Once you prioritize, integrate, analyze. And once we do that, let's take these systems to an asset owner or city scale. How can we enable you to monitor at scale? Which is what takes us to the 4th phase, is once we reach this decision intelligence state, which we're not really in, It's happening on a few projects across a few pilots. We can move from assets to cities. We can move from networks to ecosystems. And we can enable this in anything: metros, super tall structures, dams, tunnels, heritage sites. Today, one of the conversations we're having in India is that we have so many monuments. How do we make sure the monuments survive for the future generations? How do we monitor the health of those monuments? And again, here we're not doing satellite monitoring because the monument is not that vast, but we're starting with LiDAR. And accelerometers, again, to look at the natural frequency of the monitoring with the environmental context. Another great conversation is coastlines today. So with the Coastal Ministry of India, we were having a conversation that there are a lot of villages across India's coast, and Dubai is also on the coastline, and you have a lot of rigs or offshore plants in Saudi as well. And there's a lot of settlement. But the problem in India is not settlement of private organizations, but it's the villages that are getting sucked in because of climate change and sea level rise. And a lot of our port infrastructure is by mountains where there's landslides. So when it comes, there's two angles to this. One is the safety of the people in the villages. Second is the efficiency of our ports. So how do we use remote sensing at scale, again, to prioritize the places that we need to monitor through the environmental context, and then monitor the ports as well for settlement, etc., to build this coastal framework, both from the community side, but also from helping our trade and routes. Because if there's a landslide and the trucks can't make it to the port, that's money gone down for the Indian government at scale. If there's settlement on a site for a property or offshore, that's money gone down at scale. But today, as Professor Soga shared as well, there's ways to predict that, ways to enable the organizations to make better decisions. And if we make those better decisions, we also enable the community at scale. Because with the same system, we can have an evacuation system for the villages in that landslide-prone area. With that system, when we're monitoring about 200 dams in India, we know when to close the floodgates or not. So the technology exists and the integration exists. So where we're going as a technology company, as an ecosystem, I think right now we're building these decision intelligence workflows at project levels. Where we see this going is that in the next year or two, we see city-wide baselines. We're already seeing that with the Blue Line example. Then we see predictive lifecycle management coming in as a very common practice for critical assets. Engineering great digital twins and adding the socio-technic digital twins will become a reality. And at the end of the day, how do we take national level infrastructure intelligence at scale? Because as nations, our road networks, our rail networks, our buildings, our citizens, the energy that we get from dams, the mining is all very critical. And today we can prioritize and monitor what matters, how it matters, and enable better decisions even outside day-to-day construction projects. And what winning looks like for us is having 10,000 of Dubai's assets from different areas on one platform, with academia validating that results in the intelligence, with consultants improving their designs. And just as a short insight is that we normally over-design for safety. When we over-design for safety, we pour extra concrete. And I think this was a few years ago on one of the Dubai metro stations, we had inclinometers installed, and they showed deviation. And of course, the first problem was, is this data correct? But the data was correct. And the reason for that deviation was that it was over-designed and the grouting was more. So what resulted was using less cement, less time, and enabling the station to be built with the same safety standards. So again, we can optimize design and save cement. Saving cement equals to save the environment. So there's so many benefits that we can do with this decision intelligence. So asset owners prioritize, consultants optimize design, construction managers have more good nights and sleep peacefully during a project is going on, and have auditability in the decisions that we make as we move from intelligence to governance. And connected data creates awareness, and decision intelligence creates trust amongst a very fragmented industry that we're trying to make into an ecosystem through forums like Save the Buy. And that trust between all of us is when we really start taking responsibility for infrastructure safety. That trust that the data coming in is helping me make a better decision. That trust that the design will be completed on time. That trust that we are impacting a larger purpose than just building, finishing, embedding. So thank you so much for your time.